अस्सलाम वालेकुम। आप लोगों को मेरी आवाज़ आ रही है? अस्सलाम वालेकुम जी, मेरी आवाज़ आ रही है क्या सबको?
Yes, sir.
ओके। इज द स्क्रीन विजिबल टू ऑल?
Yes, sir. Okay.
ओके। ओके। बाकी क्लास किधर है? वी ओनली हैव 5 पार्टिसिपेंट्स अदर देन मी। सो बाकी सारे कहाँ हैं? विल वेट फॉर 1 to 2 मिनट्स और फिर हम लैब को प्रॉपर्ली स्टार्ट करते हैं। टेक्स्ट इन योर व्हाट्सएप ग्रुप्स कि एज सुन एज पॉसिबल सारे के सारे ज्वाइन करें। ओके। जी, समरा, मलाइका, रुमैसा, साकिब, लारेब, प्लीज सारों को टेक्स्ट करें कि वो एज सुन एज पॉसिबल लैब को ज्वाइन करें।
सर कर दिया।
ओके। ओके, सो आई विल स्टार्ट एंड आप लोग बीच में मुझे बता दीजिएगा इफ यू फेस एनी प्रॉब्लम रिगार्डिंग ऑडियो या वीडियो। ओके। सो जी, एम आई ऑडिबल टू ऑल? एम आई ऑडिबल टू ऑल? इज द वीडियो एंड द ऑडियो क्लियर?
Yes, sir.
सर।
ओके। So this lab is about effect of poles and zeros on time response. So the reference is same, the control systems book that we are going through in our course right now. So basically, we'll add a pole to the system and see its effects on the system, and then we'll add a zero to the system and see an effects. So the very first thing that we are going to set up is a first order function. You can see a over s plus a. So this transfer function would be set in MATLAB, and you will change the values of a for 1, 2, 3, and 4. And for each value of a, you're going to plot the step response against each of the four transfer functions. That means 1 over s plus 1, 2 over s plus 2, 3 over s plus 3, and 4 over s plus 4. So you are going to plot the four step responses. How? You're going to do the same num transfer function command. A is equal to tf, the numerator is 1, the denominator is 1 space 1. In the case of 2 divided by s plus 2, your numerator is 2 and the denominator bracket would be 1 space 2. Similarly, in the case of 4 divided by s plus 4, the numerator would be 4 and the denominator would be 1 space 4. Then you are going to do the step response. You have to plot the step response for each of the transfer functions. And how are you going to do that? You are going to use the command ltiview. Ltiview. If I can write this over here, just a second. Okay, is the whiteboard visible to all of you? Is the whiteboard visible to all of you?
Yes, sir.
Yes.
Okay. Okay. So the command that we are going to use is A is equal to TF, and then we are going to write numerator and then the denominator. So in the case of A over S plus A, in which A is equal to 1, we'll have 1 over S plus 1. In case of 4, we'll have 4 over S plus 4. So 4 over S plus 4 would be written as 4, 1 space 4. This means what? This means 4 over S plus 4. So now I want to have a look at the step response of the system. So I'll write LTI view, and in brackets I would write A. So this would give me the step response for this system. And I'm not going to put semicolon ahead it, because if I'll put semicolon, it won't show me the LTI view. So I'll remove the semicolon from this side and I'll put it in MATLAB, and I have to do this for 1 over S plus 1, 2 over S plus 2, 3 over S plus 3, and 4 over S plus 4. Is that clear to all? I guess this
सर
is
एक बार फिर
something-
बता दें.
Okay, I'm telling it again. So basically, in this lab, we're going to add poles to our system, add zeros to our system, and then see the effect of those additions on the responses, step responses. So in the first task, we are going to do A over S plus A, in which we are going to put the value of A equal to 1, then equal to 2, then equal to 3, then equal to 4. So the transfer functions would be A 1 over S plus 1, 2 over S plus 2, 3 over S plus 3, 4 over S plus 4. And we are going to view all of them in LTI view. This command LTI view over here, this shows us the step response of this transfer function that is going to be made over here. So this transfer function would be right now would be 4 over S plus 4. So what are we going to do in that specific transfer function in the LTI view? We are going to compare the responses. And how are we going to do that? We're going to right click on the LTI view, the graph, and whenever we are going to right click on the graph, an option would appear that would say characteristics. So in the characteristics option, you are going to tick the settling time and the rise time. So the rise time, settling time, and overshoot are going to be compared for each of the 1 over S plus 1, 2 over S plus 2, 3 over S plus 3, and 4 over S plus 4. So in these four systems, we are going to compare the rise time, the settling time, and the overshoot. And how are we going to do that? We're going to right click on the LTI view. And after clicking right on the LTI view, we will be given options, the pop-up window. And in that pop-up window, we would select characteristics. And in those, in the characteristics, we would select settling time, overshoot, and rise time. And then we'll compare the value of these three in all of these four systems. And then we'll be able to analyze that what is happening in 1 over S plus 1, 2 over S plus 2, 3 over S plus 3, and 4 over S plus 4. So basically, these four systems have poles at four different locations. One has at -1, the other one has at -2, the other one has at -3, and the last one has at -4. So what is the effect of moving the pole from one location to other location? We'll be seeing this effect over here in the lab task number 1. So I want all of you to open your laptops, and then we'll observe that what is the difference. You'll do this on MATLAB and share the results, share your screens over here with me. The next task is, okay, is this task clear?
Yes, sir.
Okay. So the next task is that you have to set up this system in Simulink, this B over S square plus AS plus B. And you're going to use the transfer function block, and you're going to set it in feedback, or yes, no, you're not going to set it in feedback. You're going to set it as a forward transfer function only. So B is equal to 25, A is equal to 4. So the transfer function that you're going to do right over there is 25 over S square plus 4S plus 25. Is that clear? So for the system of 25 over S square plus 4S plus 25, you are going to plot the step response. How you're going to do that? You're going to put input of the system as step, and after that you're going to put scope. So you're going to plot it, and when you'll run the system, the step response would be visible to you, and you're going to observe overshoot, settling time, and peak time. So settling time, overshoot, peak time, and rise time. So four things. So for the system number 1, 25 over s square plus 4s plus 25, you're going to observe percentage overshoot, settling time, peak time, and rise time. Now you have to change the system in such a way that imaginary part of the poles remains the same, but the real part is increased 2 times. So as far as the imaginary part and real part is considered, how you're going to do that? Remember the lab number 1 where we had the command roots. So you are going to extract the roots of 1 in those specific roots, you are going to keep the imaginary part same, but you are going to increase the real part 2 times. So how you are going to do that? I'm showing you an example. Okay. So you're going to do that by roots of 1, 4, 25. Okay. So this would give me some roots like 2 plus 4 iota and 3 and 2 minus 4 iota. So these are the two roots, for example, I get over there. So what I have to do is that I have to keep the imaginary part same, but double the real part. So how I'll do that? 4 plus 4 iota and 4 minus 4 iota are my new roots, because I have kept the imaginary part that is over here same, but I have doubled the real part. So the real part was 2, but the imaginary part is same. So now what I'm going to do is I'm going to use the command poly, and I'm going to construct a new polynomial with these roots. So I'll put 4 plus 4 iota, and in the MATLAB you're going to put static over here. And next is 4 minus 4 static iota. So basically this command would give me the new polynomial. For example, let's say that the new polynomial comes out to be 2756. Just an example. So what I'm going to do next is that I'm going to change my transfer function that I have put over there, that was 25 over s square plus 4s plus 25. Now I'll change that transfer function to 56 divided by 2s square plus 7s plus 56. So the new transfer function would be 56 divided by 2s square plus 7s plus 56. And now I'm going to do the same thing. I'm going to put the step input and put a scope at the end of that input. I'm going to run that system, and that scope would tell me the output of that system. Again, I'm going to record the percentage overshoot, the rise time, and the settling time. So this would give me an analysis that when I'm going to increase the real part of poles and keep the imaginary part same, what happens to these responses. Similarly, the next part of this, let me show you. The next part says that you have to change A and B such that imaginary part of poles remains same, but now the real part is decreased to half. So this means that now my polynomial would be made from poles that are 1 plus 4 iota and 1 minus 4 iota. Why? Because the original poles were 2 plus 4 iota and 2 minus 4 iota. So I'm only giving you this example. I'm not giving you the real values that are going to come. I'm giving you just an example that maybe, let's suppose this is the value. So that would be 1 plus 4 iota and 1 minus 4 iota, considering that the original poles were 2 plus 4 iota and 2 minus 4 iota. So considering this system, I'll be making a polynomial from -1 plus 4 iota and -1 minus 4 iota. A polynomial would come out, and that would tell me the changed value that I have for my transfer function over here. So basically, in this task, I'm going to have three systems. 25 over s square plus 4s plus 25, system number one. I'm going to observe the output for this system. Then I'll have the second system in which the polynomial would be made by increasing the real part to double and keeping the imaginary part same. And similarly for A and B, such that the imaginary part would remain the same, but real part is decreased to half. So these three systems would be compared in terms of overshoot, settling time, peak time, and rise time. And I'm going to construct these systems on Simulink, and I'm going to put the step as an input, and the output would be scope. So I would be observing the output on scope and making comparisons over there by making a table in the lab report. I'm going to need some analysis from you guys that what happens when we keep the imaginary part same, but the real part is doubled, and what happens when we keep the imaginary part same, but real part is halved. So what is the effect on these overshoot, settling time, peak time, and rise time for each of these? So for those of you who don't know how to observe this percentage overshoot, settling time, peak time, and rise time, I'll upload another tutorial for you that would be a revision tutorial that on your GCR that would show you how to measure or how to show percentage overshoot, settling time, peak time, and rise time on scope. So any questions till now, till this task number 2?
No, sir.
Okay. So we have task number 3 over here. So in this task, it's quite similar to task number 2, where we had increased the real part and then decreased the real part, and we had kept the imaginary part same. So now the difference is that we are going to keep the real part same, but imaginary part is increased 2 times and imaginary part is increased 4 times. So in this system, what we're going to do is that I'll show you this on the whiteboard again. Okay, so here what we are going to do is that we are going, for the example, in this system, what we did is that the roots came out to be 2 plus 4 iota and 2 minus 4 iota. So we increased the real part to 4, that is, we doubled it and kept the imaginary part same. So now in this case, what we're going to do is that, for example, we have the roots of again 1, 4, 25, and the roots come out to be 2 plus 4 iota and 2 minus 4 iota. So we'll make a polynomial from, you need to focus on this. I'm going to make the new polynomial from 2 plus 8 steric iota and 2 minus 8 steric iota. So what does it mean? Also, you are going to have negative real parts, so that would be -2 over here. Similarly, you'll have -2 and -2 over here. So what have I done over here? I have kept the real part same, that is 2, and I have increased the imaginary part by double. So the imaginary part that was 4 before is now 8. Now let's say the polynomial comes out to be 5, 25, and 100. So my new transfer function would be 100 divided by 5s square plus 25s plus 100. Similarly, I'm going to increase the imaginary part 4 times. So that means that my poles would be -2 plus 16 iota and -2 minus 16 iota. Then a polynomial would come out and I would make the transfer function using that specific polynomial. So my polynomial would be changed every time I changed my poles, every time I change my roots, and that would give me the new transfer function that I'm going to have over there. So that would tell me that I have changed my transfer function, and the transfer function would be changed by changing the imaginary part and the real part. I'm going back to the manual. Okay, so now my transfer function would be for same real part, but double imaginary part, and same real part, but 4 times imaginary part. So I am going to have three systems. One is the original system, 25 over s square plus 4s plus 25. Then the system with double imaginary part, but same real part. Then the system with 4 times the imaginary part, but same real part. Now what I'm going to do is I'm going to have a comparison of percentage overshoot, settling time, peak time, and rise time. I'm going to do the same, that I'm going to make a table for the values of percentage overshoot, settling time, peak time, rise time for all of these three systems. And then I'm going to make an analysis, a comparison, that what have I observed in these systems. So after I do this, I'll be able to analyze that what happens when poles move on the imaginary axis, keeping the real axis same, and what happens when I move the poles on real axis, keeping the imaginary axis same. So any questions till now, till task number 3?
No, sir.
Okay, so the last task that we have to do over here is that he says keep the b s square plus as plus b same 25 over s square plus 4s plus 25. Now he says that we have to maintain a transfer function such that in part number 2 that a and b should be altered such that the damping ratio remains the same, but the natural frequency is increased 2 times, and a and b are selected so that the damping ratio remains the same, but natural frequency is increased 2 times, 4 times. So what is this damping ratio over here, and what is this natural frequency over here? This is something that we needed to discuss in the on-campus lab, but since we are over here, so no worries. I'll do this over here so that you can understand. Okay, so the whiteboard is over here.
सर आप समीर को अलाउ कर दें, वो क्लास में नहीं हो रहा।
Yes, I've done it. Okay, can you see the screen?
Yes, sir.
Okay, am I audible to you?
Yes, sir.
I'm audible? We have this transfer function over here. Omega n square divided by s square plus 2 zeta omega n s plus omega n square. So here we have two factors. One is omega n and the other one is zeta. Omega n is the natural frequency. I'm going to write it over here. Natural frequency. And zeta is damping ratio. Okay, so in this omega n square divided by s square plus 2 zeta omega n s plus omega n square, this is the standard form of transfer function. Omega n is the natural frequency and zeta is the damping ratio. So you're going to compare your original transfer function 25 over s square plus 4s plus 25 with this transfer function that I have written in front of you. So omega n would be replaced by omega n square would be replaced by 25. That means your original transfer function was 25 divided by s square plus 4s plus 25. So that means that in space of 25, you have omega n square. So this means that your omega n is equal to under root 25. That means omega n is equal to 5. So in the same method, in the same way, you are going to find out the value of zeta. How? 2 zeta omega n is equal to 4. This 2 zeta omega n is replaced by 4. And we know that omega n is equal to 5. So you'll find the value of zeta over here as well. Now you are going to do what? You are going to replace the values. You are going to replace the values by this, that the A and B are done so that the damping ratio, that is zeta, remains the same, but natural frequency is doubled, and A and B are changed so that the damping ratio remains the same, but natural frequency omega n is increased 4 times. Is this clear to all?
स्क्वायर से डबल कैसे हो सकता है? तो
I can't hear you. दोबारा बताएं क्या कह रहे हैं?
सर जैसे वहां पर तुम बताया ना 25 मतलब अंडर रूट ले लें तो 5 आ जाएगा। दूसरा मतलब कोई भी नंबर लेते हैं सर, उसको मतलब एक नंबर को मतलब वो डबल कैसे हो जाएगा और 4 टाइम कैसे इंक्रीज करें?
कोई भी नंबर नहीं ले सकते हैं, वो नंबर हमने लेना है जो कि नंबर हमारे पास यहाँ पर ओरिजिनली गिवन है। जैसे ये है 25 ओवर एस स्क्वायर प्लस 4s प्लस 25, ठीक है। तो 25 ओवर एस स्क्वायर प्लस 4s प्लस 25 में हमारे पास ओमेगा एन और जीटा की वैल्यूज यहाँ पर गिवन है। Is that clear? Is that clear?
Yes, sir.
Okay, start doing these tasks. आप MATLAB पे काम करना शुरू करें और फिर मैं आपको I'll end this session and I'll start again. You have to bring your laptops and share the screens with me, and then we'll complete this lab over here. Okay, I'll start the session again in 15 minutes. I'll upload this recorded lecture on GCR as well. Okay. Okay, so bring your laptops. I'm going to end this meeting and we'll start again in 15 minutes.